Okay, complete the truth table for this logic circuit. When x is 0 and y is 0, the AND gate will give us a 0, and the XOR gate, remember this is the XOR gate, and the truth table for XOR gate is 0 0 would give us 0, 0 1 would give us 1, 1 0 would give us 1, and 1 1 would give us a 0. So when both inputs are the same, then the output is 0. When both inputs are the same, then the output is 0. So this is the truth table for XOR gate. Okay, so when both inputs are the same, the output is going to be 0. So A is 0, B is 0. When we have this condition 0 1, this would be what? Y is 1. 0 1 would give us 0 at the AND gate, and 0 1 would give us 1 at the XOR gate, right? So XOR output is going to be 1. So this is going to be 0 1. And when we have 1 0, when we have 1 as x and y is 0, then AND gate will still give us a 0, and the XOR gate will give us 1, which means what? A is 0, B is 1. And when we have 1 1, AND gate output will be 1, right? And both inputs are the same, so XOR is going to give us 0. So this is going to be 1 0. So that's our table. Now you should know this by heart. This is a half adder circuit, right? This is a half adder circuit, meaning it can add 2 bits and give you the result for 2 bits. Okay, then I'll just explain that in a bit. So the name of this circuit is a half adder circuit. Okay, let me quickly explain why we call this circuit as the half adder circuit. Why is this circuit called the half adder circuit? Okay, now for example, in binary, if you were to add 0 plus 0, what would be the sum value? You'll get 0 as the sum and you'll get 0 as the carry. Okay, so if you were to do 0 plus 1, then you would get what? 1 as the sum and there would be no carry, right? If you were to do 1 plus 0, if you were to add these 2 bits, 1 would be the sum and you'd get no carry. But if you were to do 1 plus 1, right? If you were to do something like this, 1 plus 1, if you were to add these 2 bits, you'd get 0 as the sum and 1 as the carry, right? So this would be your carry. So 0 as the sum and 1 as the carry. Okay, now if you take a look at this column right here, then you can see that this column is the same as this column. And if you take a look at this column, you can see that this column is exactly the same as this column. Meaning what? Meaning the AND gate is giving us the carry value of addition, right? And the XOR gate, the output of the XOR gate is going to give us what? Is giving us the sum part of the addition, right? So if you take a look, when the input is 0 0, we get what? 0 carry, 0 sum. When the input is 0 1, we get 1 as the sum and 0 as the carry, right? And when the input is 1 0, we get 1 as the sum and 0 as the carry. And when the input is 1 1, we get 0 as the sum and 1 as the carry. So you can see that this is a half adder circuit. It can add 2 bits and give you the sum and carry. Now he's asking us to name the labels that we can give to A and B. Well, we can say that instead of this as being A, we can say that this is the carry. This output we can call as carry, and this output B we can call as sum. So we can say this is carry and we can say this is sum. Okay. And now he's saying explain why your answers are appropriate for these labels. So why is this an appropriate label and why is sum an appropriate label? Okay, so the label carry represents the carry part of the addition of 2 bits, and we've used the label sum because that represents the sum part of the addition of 2 bits. Okay, let me quickly explain the difference between a half adder and a full adder. See, a half adder is only going to add 2 bits, so 0 plus 1, or for example you have 0 plus 0, or 1 plus 1, or 1 plus 0. It just adds 2 bits. That's the half adder. The full adder, however, takes into the account the fact that you may have a number like this, right? And when you're adding this number, the result of this addition might be a sum and a carry value. So you can't just add 2 bits. You need to make sure that you need to make sure that you account for the carry bit also. So in this case we have 3 bits, right? And this would result in what? This would result in a 0 here and another carry, and once again in this case we need another 3 bits. So the calculation is not always limited to 2 bits. Sometimes we have to add 3 bits together to get to the result, right? So the full adder takes into account this consideration. Okay, let me explain a little bit more about the full adder. See, in an addition like this, we have these bits that are going to be added, and in each case we might get a carry also, right? So we may end up having 3 bits to add here, 3 bits to add here, and 3 bits to add here. What we can do now, what we should understand now, is that for each of these we need a full adder. So we need a full adder circuit to add these 3 bits. We need another full adder circuit to add these 3 bits, and we need another full adder circuit to add these 3 bits. Okay, and as far as this is concerned, this can be accomplished using a half adder circuit, because this is only 2 bits, right? But the general practice is that we assume that the carry bit in this case is 0, so we even make this one into a full adder circuit. We assume there are going to be 3 bits here. So an addition like this is going to require 4 full adder circuits. Okay, I have not shown you what the full adder circuit looks like. I'm going to do that in a bit. Okay, but I hope you understand this. And if we have something like this, 0 1 1 0 1 0 1 1 1 0 0 0, in this case we have what? 6 bits, right? 6 bits. So these are 6 bits and these are also 6 bits, right? So in this case we are going to require what, right? We are going to have a carries here, right? So in this case we are going to require 6 full adder circuits to be able to add this number up. Okay, let me show you quickly how to draw the full adder circuit diagram. For a full adder circuit diagram we just need 2 half adder circuits, okay, and we're going to link these up, and the linking is pretty simple. The XOR gate output from the first half adder goes to the XOR of the second half adder, okay, and this second input is basically the carry bit, okay. So this XOR is going to receive one input from the previous XOR, and the other input is going to be the carry bit. Okay, as far as these two AND gates are concerned, their output is going to be given to an OR gate. So this is an OR gate, right? Okay, and this is going to be the sum part, and this is going to be the carry part of the full adder, right? So it's as simple as this. Let me draw this once again so that you can memorize this. All you require for this is 2 half adders. So I'm just quickly going to draw a half adder. It's an XOR circuit, XOR gate with an OR gate, right? And I'm going to draw another half adder, XOR with an OR gate, with an AND gate, right? XOR and AND, right? And this is going to be input here. The carry bit is going to be input here, right? So this was X and Y, and this is the carry bit, and between these two AND gates we are going to put what? an OR gate. So that's our full adder circuit. So this is the sum part and this is the carry part, right? So this is your full adder circuit diagram. Okay, sometimes a half adder is simply represented by a box saying that this is a half adder, right? And this takes two inputs, x, y, and gives out sum and a carry value. Similarly, a full adder can also be represented by this box saying that it takes two inputs, x and y, and it takes a carry also, right? It takes a carry bit also. So this time there are basically three inputs, the carry, x and y. So and the output is always going to be sum and carry, right? So that's a full adder for you. Okay, sometimes you may see a circuit like this, and this circuit has four full adders, right? You can see that this has four full adders, which means what? Which means a circuit like this can do an addition like this, 0 1 1 0 1 0 1 0. So it can handle addition like this where each number is made up of 4 bits, right? So this circuit is meant for an addition of two 4-bit numbers, right? And what we can clearly see here is that, you know, this should be 1 and this should be 2, sorry. Okay, so this should be S2 and this should be S3. Okay, so what we can see here is that, you know, there are three inputs to this, and this is the sum output. The carry output is being fed to this full adder, right? So the carry output from the first addition is being fed here, right? That's what we are doing here. So the carry comes here, right? And now this has three inputs, and the sum part is here, and the carry output from this is being fed here. So the carry output from this is being fed here, right? So we can see that we have a full adder circuit that can add two 4-bit numbers, right? Two 4-bit numbers. Okay, so I hope you've understood the concept.